In this video, I want to explain the spiral antenna, its mainly useful properties, and why it's important. So, a spiral antenna, we can kind of derive or figure it out from starting with a dipole antenna. So, here we just have a simple linear wire antenna, and let's say we take the arms and wrap them around each other. So, take the first arm, just begin to curl it around itself, and then the second arm would kind of go in the same way. So it turns out when we do this, we end up with a lot of very nice properties. So one of which is very wide bandwidth. So for instance, the fractional bandwidth can be up to 40 to 1, 10 to 1 is very typical, but you can end up with easily 30, which is the ratio of the highest frequency that the spiral works at to the lowest frequency. So for instance, if the lowest frequency is 1 gigahertz, this spiral antenna will be in band all the way up to 30 gigahertz, and that's very useful. Another property is that spiral antennas are circularly polarized, which is useful in such applications as GPS. And you can determine the sense of polarization using your hand and figuring out which way it wraps. So in this, if you put your finger in the direction of radiation and figure out which way you'd have to curl your fingers, if you use your right hand in this case, it goes in that sense, which means this is right hand circularly polarized. If you flip this over, you'd find that it would wrap the other way with your left hand, and so the radiation into the page would be left hand circularly polarized. So the radiation is normal to the plane, so it would be up in this direction and also down, unless it's cavity backed or backed by some metal. Impedance, the circular polarization and bandwidth is fairly constant with respect to frequency, which makes it useful. So let's talk about how this is designed. So commonly, one of the more common ones is this log periodic spiral. And so what that is just each arm is defined by a polar function like this, where the radius grows exponentially with phase. So for instance, here we have R0, which is the minimum radius, where the spiral starts to turn. And as you increase phi, the angular spin here, the radius grows exponentially. So that's how you get this arm. And then the second arm is just out of phase by 180 degrees, or pi radians, and so that's the second arm. Another common spiral antenna is this Archimedean spiral. This one has a radius that grows linearly with phase. A is a parameter that determines how quickly it grows. So for instance here it's just increasing at the same rate as you go out. So once we have the function or plot of our spiral antenna, we can figure out some of the radiation properties just by looking at it. So first we look at this minimum radius R0, and that'll determine actually the highest frequency. So in here, R0 is this minimum radius where it starts to spiral. So it turns out the highest frequency, call it F high, occurs when this radius is about a quarter of a wavelength. So let's just say R0 equals lambda over 4, which is C over 4 highest frequency. So the highest frequency occurs at C0, the speed of light, over 4 R0. Similarly, we can find the outer radius, which is called R spiral, determines the lowest frequency. So it turns out that when the circumference of a spiral is equal to one wavelength, that'll determine the lowest wavelength. So here we have the circumference, C, is 2 pi R spiral, and that should equal lambda, which should equal C0, the speed of light, over the lowest frequency. So we can solve and get the lowest frequency, C0, the speed of light, over 2 pi outer radius of the spiral. So this determines the lower and upper frequency. Another design parameter is this parameter A, which describes how quickly the spiral grows. Large values of A, it grows very quickly. A is small, it's much tighter. Commonly A is 0.1 to 0.3, with like 0.2 being pretty typical. The number of turns is also a parameter, how long far out you want to take the spiral antenna. Anywhere from 1.5 turns to 3 is usually pretty common. And then how you feed it, the feed structure, and I'll show an example of an infinite balun, which is commonly used in spirals later. Now this is a differential feed, which means the current is flowing out of the positive end and into the negative end. So the current, in this sense, is 180 degrees out of phase on this arm versus this arm. So when we get out to the point where the circumference is roughly lambda, circumference equals lambda, then this outer arm is roughly a half wavelength, and this arm is roughly a half wavelength. Now, let's say the current is flowing outwards on this arm, so in the whole half wavelength the current will be going in the same phase. Then on this arm the current must be flowing inwards because it's going to be 180 degrees out of phase with this arm. So on this whole half arm we have the current going this way. So here, if we look at this, we have the current here and here are adding in phase. The current here and here are adding in phase. So it's this, when the circumference equals lambda, we end up with this arms that are adding in phase and therefore producing the radiation. So this also explains why we have circular polarization. Is one, we have these two currents radiating, and then we have 90 degrees away, we have this set of currents radiating. And this set of currents are 90 degrees rotated in position or direction, and 90 degrees out of phase in time. So the two things together make circular polarization. So as we go higher in frequency, this one wavelength condition occurs closer to the center of the spiral. When we have this good radiation property where everything's adding in phase, the currents are producing radiated E fields and H fields, and so the energy is lost. As a result, as you get outside one wavelength for a given frequency, the currents die off pretty quickly because the energy is lost to radiation. As a result, since the currents are dying off as you go out of the spiral itself doesn't need to be infinitely long. You can terminate it such that, because there's going to be little reflection from the end if the current is losing all its energy to radiation. So that's the fundamental mechanism for why the spiral antenna radiates. So I threw together the spiral antenna, so you can print out from this webpage some plots so that you can overlay your own spiral antenna if you want. So I took 2 coaxial cables here just to make up a quick spiral antenna, and then I used one as the feed, and then attached the center conductor of the feed coaxial cable to the outer conductor of this second arm of the spiral antenna. So here I just printed out an Archimedean spiral antenna, and then used 2 coaxial cables to make the antenna. It's important to use the same type of material for both arms. You don't want to use like one thin conductor and one fat conductor, because you really want this balanced condition of current on both arms to produce the radiation that we're looking for. So doing this, I find the smaller arm, the inner radius was given as about 25 millimeters, and the outer radius was 60 millimeters. So if you go through and look at the equations that we discussed that determine the high and low frequency, find that 25 millimeters would correspond to a highest frequency of about 3 gigahertz. 60 millimeters outer radius would define the lowest frequency in the band, and that turns out to be about 800 megahertz. So I threw this thing together, this little spiral antenna, and I measured the VSWR, and here's what I got. So you see it's kind of erratic up until about 800 megahertz, and then it starts to become fairly flat. So this is VSWR versus frequency. Here is about 700 megahertz, and up here is about 3 gigahertz. And so we see we get this reasonable property of constancy with respect to frequency. So as you can see, even doing a pretty crappy job just throwing together an antenna, we can get very wideband properties that radiate pretty